Hey guys, Kenny here. Today I wanted to do a quick review over chemical reactions. You should have probably gone over this already in your physical science class, but I wanted to go ahead and do a little short lecture on it anyway, just to make sure we had all the pieces in place, because it'll be helpful for us as we go ahead and start talking about cells and how our cells use energy. Now, a chemical reaction is going to be a really important piece of what keeps maintaining life. When we were looking at the characteristics of life, we said the use of materials and energy is a key factor or characteristic of life. So, what are our essential questions for today? Number one, what is the relationship between the reactants and the products in a chemical reaction? Okay, so those terms hopefully are ones that you already know. If not, they should probably be in your notes. Number two, what are the similarities and differences between exergonic and endergonic reactions? Now, for some of you, you may not have heard these terms, exergonic and endergonic, but instead did exothermic and endothermic. I'll talk about why I use this slight variation of it, but the similar in terms of their meaning. And three, what is activation energy and why is it needed? Now, most of you at some point have sat around a campfire, watched the flames flicker in a fireplace, something along those lines. The burning of wood is a chemical reaction, and this process changes one set of chemicals into a different set. The chemical reaction always involves changes in chemical bonds that join atoms in the compounds. Okay? The elements or compounds that enter into the chemical reaction are called the reactants. These bonds that create the reactants are going to be broken apart and reformed into the elements or compounds produced by a chemical reaction, which are called the product. So we're breaking bonds in the reactants to form new bonds in the products. So if we go back to our campfire analogy, as wood burns, molecules of cellulose, which is what the wood is primarily made of, are broken down and combined with the oxygen in the air to form carbon dioxide and water vapor releasing energy. Now this energy comes in the form of both light and heat, and we could keep going on this whole trend, but I'm hoping you remember some of this from your previous knowledge. So, based on what we just went over, what are the reactants when wood burns? What are the products when wood burns? What kinds of energy are given off when wood burns? Does wood burn all by itself? What must you do to start a fire? And what does this mean in terms of the energy of the system? And then five, once the fire gets started, it keeps burning. Why don't you need to keep restarting the fire? So let's go back to our previous slide. What are the reactants in the wood? Where are the reactants? That's right, that's what you start with. Okay, so if we go back here, we start looking at the reactants are what you begin with. As wood burns, you have your molecules of cellulose, so you have cellulose, and they combine with oxygen. So your two reactants in this particular chemical reaction are cellulose and oxygen. And they're going to combine to produce the next question, what are the products? In this case, they form after the fact, carbon dioxide and water vapor. These are our reactants, plus the energy released off. Now, what kind of energy is released when wood burns? Well, hopefully, having sat in front of a fire, you know that this is heat and light. Question number 4 is interesting, though. Wood doesn't burn all by itself. So if you have a log there, it doesn't just boom, burst into flames. And it's a good thing because the paper that you may be writing on right now, or that you list seen and written on in the past, is made up of wood. And if you had that paper, it would just burst into flames. But this kind of spontaneous combustion does not occur. So what does this mean? It means it needs some energy source to start the reaction. Okay? In this particular case, maybe you have a lighter, maybe you have matches, maybe you have something, or if you go back to survival strategies, maybe you have a bow and drill. Okay, maybe you have a flint stick. Whatever it's going to be, you need some energy source to kickstart it. All right, but once it starts burning, you don't need to keep doing that. You don't need to keep feeding it matches. Okay, and we'll talk a little bit about why that occurs. So we just went over a chemical reaction. We changed one set of chemicals, the reactants, into another set of chemicals, the products. Some of these reactions occur slowly, think about something rusting, and others occur very rapidly, such as hydrogen lighting in the presence of oxygen. Huge explosion very quickly. Now, regardless of the reaction, how fast it occurs, we're always going to have the same basic steps. You begin with what you have at the beginning, and that's the reactants, and those are going to be broken apart and recombined into new materials that we call the products. Okay, so breaking bonds in the reactants, forming new bonds in the products. Let's do another chemical reaction. This is one that your body uses. It's the formation of carbonic acid. This allows us to transport carbon dioxide throughout your bloodstream. And so this reaction is CO2 plus H2O yields H2CO3. So take a minute, pause. Which of the molecules are the reactants? Okay, now which ones are the products? So hopefully you were able to figure out that these are the reactants, the CO2 and the H2O. This is what you start with. If you're unsure how to tell in a reaction like this, one of the things you can look for is the arrow. The tail of the arrow right here will point towards where it starts. This is the reactant side. The head of the arrow points to the product side. So if these are the reactants on the left in this case, these are the products on the right. Okay? Now, energy is released or absorbed whenever a chemical bond is formed or broken. Okay? Because chemical reactions involve breaking and forming bonds, they involve changes in energy. That bond is stored energy. Chemical reactions that release energy often occur spontaneously. They don't need a lot to get them going, and they go pretty quickly. However, chemical reactions that absorb energy usually will not occur without some consistent source of energy to feed them. Now, this is where those terms I mentioned at the beginning come into play. Chemical reactions are typically classified based on whether they absorb or release energy. That prefix ender there, E-E-N-D-E-R, means in. So endergonic means an energy in reaction, and these are the ones that are going to absorb energy from the environment. Exer means out, and so exergonic is an energy out reaction. These are going to release energy when they occur. Often we use the terms endothermic and exothermic, which may be what you already have heard, which only relates to heat or thermal energy, but there are other types of energy as well. Light energy is a great example. Now, there's one more key term, and to me, this may be one of the most important for our discussion we'll have in cells, in photosynthesis, and so on and so forth. Even chemical reactions that release energy don't always occur spontaneously. And this is really good because, as I mentioned before, otherwise the paper you have in front of you would burst into flames. Chemists call the energy that is needed to get a reaction started the activation energy. And this is a hugely important thing to understand, especially as we start talking about things like enzymes. Now, here is a graph of energy in a chemical reaction. So let's go over what this shows you. You can see on the x-axis the course of the reaction. So this is time going by. And on the y-axis here you can see the energy. Now you're noticing in this case, hopefully, that the reactants start at a lower energy than we have at the products. So in this case, we're dealing with energy being absorbed by the reaction so that the products have more energy stored in them than the reactants do. So all of this is energy that's being put into the chemical reaction. Now notice that it doesn't just go straight up to the products, but instead goes up to a peak and then drops down to the actual products. That point from where the reactants are to the peak is known as the activation energy. This is how much energy this reaction needs in order to produce these products. So how would this look in an energy releasing reaction? Pause and think about it for a second. When you're ready, we'll move on. Okay. Notice that the x and y axes are the same in this case, but in this case, the reactants have a higher starting energy than the products do. So instead of going straight down once again, you need some energy or activation energy to go ahead and start this chemical reaction. So going from here, you need to put energy in until you reach this peak, and then the reaction carries out by itself. So the point from the reactants to the peak, just like over here, is still known as the activation energy. Now, activation here, activation here. But in this case, the reactants have lower energy than the products, and in this case, the reactants have higher energy than the products. This is energy absorbing, or endergonic. This is energy releasing, or exergonic. All right. Hope that helps, guys. Take care of yourselves. I'll talk to you soon. So long.